Okay, so there were a couple of just little short parts that we skipped in class, and the main reason is that I just didn't want to get into super potentially confusing stuff right before the AP test. So if you will take a look at part C here. So just to kind of catch you up, we have water flowing into the pipe at this rate. We have water flowing out of the pipe at this rate. And then part C says, at what time is the water in the pipe at a minimum? Okay, so what I want you to do is, I still have my equations typed in here. So we're only looking from 0 to 8. So I'm going to go ahead and adjust my window to be from 0 to 8 as well. And then remember that my first graph that's going is going to be my in graph. So down here for part C, I'm going to set up a graph on my paper here. So here's 8, here's 0. And then the other thing that I'm going to do before I graph it is I'm going to look at my table and see what my values are. So it looks like it comes up to 17, 19, and then back down. So when I go into my window from 0 to 8, I don't need this to still go to 900 like that other problem. I'm going to make it like negative 20 to 20. Okay, about that. So let's hit graph. Here we go. So the first one is the in graph. Okay, so there it is. There's the out graph. Okay, so my in graph was here. This is in. And then my out graph was here. Okay, so I want you to think about, for this first interval of time, all the way up until where these graphs intersect, my out rate was greater than my in rate. And so I want you to think about that overall, if my out is bigger and my in is smaller, then overall the water level is decreasing. Okay? On the other side of that intersection point, it flip-flops to where my water going in exceeds my water going out. That means that in that side of the graph, my water overall is increasing. Okay, because there's still water going in and coming out, but it's going in faster than it's going out. And remember, that's why in part D we said it overflowed at 50. Okay, so I want you to think about, if I want to know, it says, when is the water in the pipe a minimum? Well, think about this point right here is a minimum because the amount of water in the tank changes from decreasing to increasing. So it goes from negative slope, decreasing, to increasing as a positive slope. Now, obviously, that's not for this graph, but like if I was doing a graph for the amount in the tank, then it would be negative overall changing to positive. So I'm going to find this point by finding the intersection, second trace, option 5, enter, enter, enter. Okay, they intersect at 3.2716. So this time is 3.2716. Now, the other thing that we had talked about is that when you're doing an absolute min or max, when you're trying to find the min or max that's not like the relative one, you need to compare it to the endpoints unless it's the only critical number on the interval, which we can see is the case for this question. These never equal each other again. So I would put minimum water occurs, spelled that wrong, at t equals 3.2716 because before this value, we'll say the out, which was d of t, is greater than r of t. So water level was decreasing. After this value, r of t is greater than d of t. So water level changes to increasing. Okay, and remember that whenever something changes from decreasing to increasing, that makes it a relative max. Then T equals 3.2716 is a relative minimum. Also, the absolute minimum, because there are no other critical numbers. Okay? So not only is it a relative minimum because the overall change is from decreasing to increasing, but it's also the absolute minimum because this is the only place where my rates switch. So there are no other critical numbers on the interval. Okay? All right. So hopefully that didn't confuse anybody. Sorry if it did. You can definitely ask me questions tomorrow if you want to. The other question that we skipped a part of, we're going to rewind back to it. And it was the one about people going into the auditorium. Okay? And mainly I just skipped it because I wanted to get through the water problem. But let's read now carefully through part C. So the total wait time for all the people in the auditorium is found by adding the time each person waits, starting at the time the person enters the auditorium and ending when the concert begins. The function W models the total wait time for all the people who enter the auditorium before time t. The derivative of W is given by boom. Then it says, find W of 2 minus W of 1, the total wait time for those who enter the auditorium at time 1. Okay, so a whole lot of nonsense there that I really don't even want to get into. I would look at the details. This is W prime. They are asking me to find W of 2 minus W of 1. So, I want you to think about for a second, if this is W prime, W is the antiderivative of W prime, right? W is the antiderivative of W prime. So if I integrate W prime of t from 1 to 2 dt, what is that going to give me? Well, the antiderivative of W prime is W, right? And then what would I do from there? I would plug in 2 and 1, so I'd have W of 2, W of 1, and then what would I do with these guys? I'd subtract them, right? So in a really sneaky way, look what they're asking you to find. W of 2 minus W of 1, they're just in a sneaky way asking you to integrate from 1 to 2. Now, you wouldn't even do that integral by hand. You do it in the calculator, right? So I am going to have to go back and type this original RFT function back into my calculator. If you still have it typed in, cool. But all that I'm really going to have to do is integrate this function here from 1 to 2. And that's going to be my answer for part C. So we are clearing out what's already typed in there. 1380 x squared, 675 x cubed. Okay, then I'm going to come down here and clear that out. Double check that it's right. Okay, so I want math 9 from 1 to 2. And then in my function, I'm going to type in 2 minus x times alpha trace y1 dx. Okay, so see how I typed that in? So it's 2 minus t multiplied by y1. And all this junk about, oh, the wait time is defined by blah, 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 nobody cares about that, okay? All just there to confuse you. So the answer would be 387.5. Okay? Then in part D, and actually let's talk about, does it tell us what this is measured in? If it's wait time, it would be measured in hours. Okay? So that means that all the people in the auditorium that entered from 1 to 2, all of them together waited 387.5 hours, which is a long time, but if it's a lot of people, then you break that down per person. It's not that much. Okay, part D. On average, how long does a person wait in line in the auditorium for the concert to begin? Consider all the people who entered from after the doors opened. Use the model for wait time from part C. Okay, this is where you would have to think about. They are asking you for an average. Okay, on average. There are only two averages. There's average rate of change, or there's average value. Okay, so I want you to think about which one that we're going to use here. Average rate of change is a slope. If they want to know how long someone has to wait, that's going to be the total wait time. Okay, that's a value. This is a wait time. I want an average wait time. So this is going to be average value, not average rate of change. So keep in mind that it says consider all the people. So I'm going to do 1 over 2 minus 0. Then integral 0 to 2. And then I'm going to integrate my wait time function, which is 2 minus t. And then my r of t, which is really my y1. Okay? So you would just have to think about, I want to do my average value. Okay? And then actually, hang on one second. Okay, we do have actually a mistake here. Okay, so I want you to think about this here is the total wait time. So if I want to figure out how long a person has to wait, I need the average per person. So I actually here, I don't need to put 1 over 2. That would be the average per hour. That's not what I'm looking for. They want the average wait time per person. So rather than putting hours here, this is a little bit tricky. This is probably the mistake they would have expected you to make. You need to divide by the number of people that are in the auditorium, not by the amount of time that's passed. So go back to part A. We already figured this out. Do you remember how many people entered the auditorium? 980 people. So it'd be 1 over 980 people, because think about it, all those guys are splitting the wait time. Like not one person waited for 387 hours or whatever, right? So I'm going to do 1 over 980, math 9. Then I'm going to set up my integral from 0 to 2. And then I'm going to do 2 minus x multiplied by alpha trace y1, and then my dx. Okay, so that means that on average, they waited about 0.77 hours. But that's per person. And if you kind of think about the units, this also should make sense, because think about, if this is the total number of hours, I have to divide by the number of people to know hours per person, right? This is the total wait time in hours. So it should kind of make sense to you that you'd have to divide by 180. So they're not actually asking you the average value formula. They're asking you the average value per person, and that's actually a different question than what you want. Okay? So hopefully that didn't confuse the crap out of you, and you're ready for your mock exam.